Today is the last day of the workshop, and today this session of mine would be the second last session of this workshop. In the later half of the day, Dr. Dheeraj Rathi would be giving the final session for this workshop. And with all of you have been with us for the last 4 days, and I would like to thank you so much for being a part of this workshop. So without delaying any further, let me start my session today on data compression in wireless sensor networks and IoT. So this talk is basically about a specific data compression technique for which you have got a glimpse of that compression technique yesterday in Dr. Verma's lesson or session. But today I'll be talking about that compression technique in detail, how that compression technique was implemented by us in in solving different problems on wireless sensor networks. So I'm Vishal Krishna Singh, and I'm an assistant professor in Indian Institute of Information Technology, Lucknow. So let us start the workshop. So before the workshop proceeds, let me explain you how this entire session will this entire session will move on. So the first and the foremost thing which we are going to discuss is I'll explain briefly about wireless sensor networks, what wireless sensor networks are, and what are sensor-based IoT networks. There are certain properties which are much desirable for any wireless sensor networks, and similarly there are so many constraints which we might have, which we necessarily have in a traditional wireless sensor networks now. So these constraints of wireless sensor networks allow us to work on these problems and optimize the performance of a sensor network in such a way that the overall lifetime of the network becomes higher, or in most of the cases the lifetime, the energy consumption, the performance is judged on different parameters, and so we try to optimize those parameters. So we shall be briefly talking about wireless sensor networks and IoT. What is a sensor-based IoT network? I will be talking about that. And there are certain desirables and there are certain constraints which will be seen. Then the compression technique, which I was talking about, this is very specific. This is only a one compression technique which we are going to discuss in this entire session. That is the compressive sensing method. This is a very popular method, and this method gained its popularity in the early 2000s. And since then, it has been incorporated. Incorporated in wireless sensor networks and sensor-based IoT. So if I say that this method gained popularity in 2000, in the early 2000, it is not that this method was not available before. Just a minute. This method was not present before, but what I mean to say is that this compressive sensing method, or the compressed sensing method, has been with us for a very long time. But in the early 2000s, researchers found a way to incorporate this, or to use this compressive sensing method into different domains or different applications of wireless sensor networks. And since then, it has been used in wireless sensor networks, not only in data communication, in routing, in localization, in optimizing the network performances, in network inferences, and so many. And it has been used in so many ways. You'll see there are several ways in which we have used it. And there are certain problems which we have identified and we have solved with the help of compressive sensing. Now, once we are done with the compressive sensing method, and there are three problems which I'll be addressing, and I'll provide a solution for that as well. So, a specific application of compressive sensing, yeah, this compression method into in a sensor network or a sensor-based IoT network is what we are going to see in this phase of the presentation. Now, if the time permits, I'll also talk about a matrix completion problem, which is, I would say, derived from the compressive sensing problem, compressive sensing method. But the matrix completion problem is a very unique problem, and it has been of great interest in the researchers. Uh, it has been of a great interest with the researchers because of the efficiency or uh, the the things we can achieve with the by solving such problems, or the practical implications or the applications of this method, or their use in real life scenario could be so diverse that it can optimize so many methods, techniques, algorithms which are being used. So matrix completion is another important thing which if the time permits, we'll be going to discuss that as well. And finally, I'll conclude the session with the concluding remarks. So before discussing anything before talking about all this compression and all this compressive sensing and matrix completion and L1 norm and all those things, let me give you a brief introduction about what wireless sensor networks are. And I'm very sure that most of you will be aware of what wireless sensor networks are, but still, for those who are who lack a background on this, let me put a picture out for you now. Okay, one more thing that I have tried to give the references and due credit for whatever figures and references I have taken from some papers and presentations. But if I have forgot at some places, like in this figure over here, I'm extremely sorry for that. And there are certain pictures which I have used from the web. There are certain pictures which I have used from several papers. Uh, and I have tried to give due credit for every picture. But if I have missed somewhere, then that's my mistake then. And I appreciate the contributors on this goes without saying that I appreciate their work and their results and everything. So okay then. So if I say what a wireless sensor network is, then in order to clearly understand the picture, the idea is very clear. And from this picture, if you can see. So okay, I'll turn off my video because okay. So the idea about wireless sensor network is very evident from this picture over here, and the picture, as you can see, is that consists of small sensor nodes. Now these sensor nodes are deployed in certain region, that is region of interest, or whatever you can say, deployed area or a region of interest, or there are different terminologies used in different literatures. But let us say this is the deployed area, the area in which these and then these nodes are deployed. So these nodes, what the purpose of these nodes are is to sense any event which might occur in its proximity. So for example, if this is a sensor node, and this sensor node was deployed into this area with the purpose of identifying any event. Now we'll talk about what events are, and how these nodes communicate, how these nodes work. But the idea is that this sensor node can sense a specific type of event, let us say temperature or humidity or pressure or anything. For instance, this carbon dioxide level, nitrogen level, or any parameter, if you can say. So the sensor node can sense a specific parameter, and based on this, these nodes are deployed into a region of interest. Now this is the region of interest now. So the idea is that once deployed, this node will be able to sense, let us say, temperature in the area in its close proximity. Right? Now, what do you mean by close proximity then? Close proximity means that this node has a certain sensing range. If I say I have a reach of, let us say, 1 meters, then what I mean to say that if anything comes into 1 meter in a 1 meter radius of my body, I'll be able to catch it. So the same goes for these sensor networks. They have a sensing range and they have a communication range. So whatever is the sensing range of this is, if this node, if an event occurs within the sensing range of this node, this event will be sensed by this node and will be reported to the sync node over here. See, if you can see the figure, it is the same thing, that an event occurred over here. Now the objective after sensing an event of a sensor network is to transmit the data from the sensed position, yeah, the origin of the event, to the sync node. So once the data has been reported to this node, the next thing which we try to do is transmit the data from this point to the sync node. Now, as you can see that this node cannot directly communicate to the sync node. Now, just for us, okay, just for a simple reason that the communication range, as I said, the sensing range is limited of the node. Similarly, the communication range is also limited. So this node can maximum, let us say, it can communicate to a maximum distance of, let us say, 100 meters, and the sync is placed, let us say, 5 kilometers from this origin node. Then obviously this node cannot directly communicate to the sync node. So the idea is that this node will form a path to the sync node with the help of all the other nodes in the communication, in this in its communication range, or it will formulate a path from itself to the sync node in such a way that these other nodes, all the other nodes of the network, cooperate with it. Cooperate with it means they receive the data, aggregate it, or process it, or whatever, or let us say just forward it to the next node into the communication channel. So if this happens, this picture becomes complete, that an event was sensed over here by this node. Since this node cannot directly communicate to the sync node, it forwards the data to the next node in the communication path. Then this node forwards the data to the next node in the communication path. Similarly, this and this, and finally the data reaches sync. Now, so this gives you a picture of what a wireless sensor networks is, and thus the definition that it is an ad hoc distribution of sensors. Now, ad hoc distribution of sensors which cooperate with each other to sense, report, or transmit the sensed information to the processing unit. Now, when I say processing unit, I mean to say the sync, because this is where any data or any node will send its information, right? So if this node has sensed anything, this will be reported to the sync. If this node has sensed anything, this will be reported to the sync. So sync is the base station, or sync is the single processing unit where all the data from the entire deployed network will be reported and will be processed. So once this data is processed, it will once this data reaches the sync, it will be processed and it will be communicated to the. Please mute your mic. Nandini Patil, please mute your mic. Okay. Okay. So I hope the idea of wireless sensor networks is quite clear over here, that what we are trying to do, we are trying to deploy a small sized sensors nodes modes into a region of interest. Now, these modes are required to sense and report the information to the sink where the data will be processed. Now, this idea is very simple, that the nodes have been deployed, they will sense something, they will report something, and it will get processed and it will get reported further. So, but we'll see how this simple idea gets complicated. But before going to that, let me explain what are the you are seeing, you are witnessing the change of the how the technology is changing every day, and we have sensors in almost everything we now use in our daily life, starting from the phone to the automatic doors, to the cars, to the proximity sensors in the cars, to the there are so many practical applications of wireless sensor networks and sensor networks for that matter. So many practical applications, for examples in in environmental monitoring, weather detection, weather prediction, I would say. We have sensor networks and sensor based IoT networks. Similarly, in military applications, the nodes are deployed for detecting enemy presence or for detecting enemy movement in a restricted area or in behind the enemy lines. Scientific research as well. So there are so many practical applications in which this sensor networks and sensor based IoT networks are being used. But it is quite evident and it is quite clear from the picture you just saw in the previous slide that these nodes, as I say, they are small, very small, extremely small, and their simple task is to sense and transmit the data. Now, as you can see, the practical applications of wireless sensor networks or a sensor-based IoT network is quite diverse. Now, consider a scenario in which a sensor node which is deployed into a volcanic area. Now, in this volcanic area, the entire objective of this sensor node is to sense and report the temperature data. Now, you cannot expect, let us say I'm the administrator of this network, and then you cannot expect me to go and change the battery of the mode once the battery has died. Can you? No, you can't, because that is a very difficult terrain, because you cannot expect any human being to go every now and then to change the battery of the of all the deployed nodes in a whenever the battery runs out. Similarly, if we are talking about a forest area, similarly if we are talking about unmapped territories behind the enemy lines or something in the military applications, as I just said, or we are, let us say, in a forest area, we are monitoring animals, we are monitoring their presence or something. But then again, you cannot expect every now and then a human being to go and change the batteries if they have run out. And because these are battery operated nodes, we cannot expect human involvement every now and then. So one of the most important drawback of any sensor network which we face, even it is present nowadays, that these are battery operated and these batteries cannot be changed again and again. So there are applications in which it is not a difficult task to change the batteries, but in a general scenario, when we say we cannot expect, or we intend to derive solution, or we intend to formulate solutions which are not affected by this failure, that is the battery failure or power failure. Again, the computational capacity of a sensor node is not that high, right? So when these modes were initially deployed, these nodes were not very computationally efficient, or not very computationally, they were not very they did not had any computational more computational powers. Nowadays, the sensor modes which we have significantly high computational ability and capability, but initially it was not the case. But even now, you cannot expect a sensor mode to perform complex computations, because complex computations would require higher computational capability. It would require higher energy, and hence if the energy runs out, the nodes becomes dead and the network goes down. So that is not suggested. So whatever kind of network we design, or whatever type of application we have, these are these are the two most primary objectives in deploying a network in any application of a wireless sensor network. That is, the first objective is to conserve power, because power, these nodes are battery operated, and hence the entire idea behind developing energy efficient solutions for wireless sensor network is that if the power runs out of a node, the node dies, and the node is the node won't be functional again. The other thing is the communication bandwidth. That is, every node has limited capacity, limited computational ability, and limited transmission capability. So once we have deployed a node, the idea is to minimize the inter-node communication or intra-node communication, or the entire communication within the network should be minimized. So with these constraints in your mind, let us move forward with some of the by identifying some of the other constraints of wireless sensor networks, because of which these problems, which we'll be discussing in the upcoming slides, because of which these problems arose. So these constraints are inherent constraints of wireless sensor networks, and they are very clear because of the inherent natures of the node. For instance, the node is battery operated and is deployed in difficult terrain. So it is quite evident that you cannot expect anyone to go and change the battery every now and then. Similarly, if a node has limited computational capability, then you cannot expect the node to lose a lot of that computational capacity in trying to communicate with other nodes of the network or trying to transmit the data. So it is quite evident that it is required to minimize the in-network transmissions. So one other thing which is not possible in a wireless sensor networks, and because of these two constraints, is we cannot expect end-to-end or per hop acknowledgements. For instance, if a data was sensed by a node at, let us say, at this point, and it was, let us say, communicated by this node to this node, let us say this node as A and this node as B, then if A transmitted its sensed information to B, then you cannot expect B to send a feedback to A that I have received the data, because this will consume energy and we can't afford that. So this is the per hop acknowledgement. Now there are multiple hops into this communication path, from this to this, from the origin to the sync node. On all of these hops, we cannot expect feedback that at any point I have received the data or I have not received the data. Or you cannot expect similar feedbacks in end-to-end feedback as well is not expected in such a networks. And the reason is quite obvious, isn't it? That the entire process will take a lot of energy, a lot of transmissions, and a lot of computational capability as well, while transmitting and receiving the information from one point to another point, and then processing this information. So because of this, end-to-end acknowledgement and per hop acknowledgements are not possible in wireless sensor networks. And this gives us another problem, that if it is not possible, how do we know that the data has actually reached to the destination? And hence it is quite desirable. It is very desirable for any developer or any administrator or any researcher to work on a solution such as the nodes send the data in accurately, efficiently, and in a fault tolerant manner. So there are certain desirable properties of any deployed network of wireless sensor networks or a sensor-based IoT. Now, the first objective would be improved monitoring and reporting of events. Now, as you see, when a sensor network is deployed, I'll go back again to this figure which I was referring to. So let us say this is a region of interest or an area in which a set of sensor nodes are deployed. Now, at any point, let us say the objective is to determine the let us say determine the presence of an animal. Let us say animal A. Then it is not the case that there will be, let us say, I have deployed the network to detect the presence of an animal, let us say rabbit. Then it is not the case that there is a single rabbit in this entire network. There might be multiple rabbits, right? So once a rabbit pops up here, there is a fair chance that another rabbit might be located here as well. Similarly on here as well. Similarly here as well. So simultaneously multiple events are occurring. Similarly, if I take another example of fire detection. Let us say if this sensor network is deployed to detect fire in an area, then I say if a fire is reported here, it is not the case that it can be reported only here. It might be the case that the fire is reported here as well. The fire is reported here as well and here as well. So this is what I'm trying to say, that at any point, the number of events might be very high, and they all are occurring simultaneously. So the entire objective of this deployment goes in vain if all these events are not detected properly. So that is why improved monitoring and reporting of events is required. That is what accurate detection of events. I'll be talking about this in detail, but let us say this is one of the most important research area in the field of wireless sensor networks and sensor-based IoTs, that once an event has been detected, or once multiple nodes in the network have detected an event, this event has to be detected properly and then reported properly, because of simultaneous number of events, simultaneously multiple events are occurring, and it is of significant importance that all the events are reported properly and accurately. So the first thing was the improved monitoring and reporting of events is one of the most desirable properties while developing or deploying a solution for wireless sensor networks or sensor-based IoT. Then the second desirable thing is the network lifetime maximization. Now it is quite clear. It should be quite clear right now that the entire network is only reliable or is functional till these sensor nodes are working or alive. Now, if a node dies in the entire network, let us say, I'll go back again to this figure, and if I say that this node dies because of the battery failure, or for some, yes, let us say for battery failure, then obviously you cannot take this path for data transmission. So out of the, let us say, 100 paths, 1,000 paths, or millions of paths over there, through this node, that one path is dead. That one path which I was talking about, now this path through this node is dead. Similarly, if I say this is another path to sync, again this path is dead because we cannot go through this node. So all those paths, let us say out of the 1000 paths we were having for through this node, now out of all the paths we were having to reach the sync node, let us say 100 paths were going through this node, then these 100 paths are dead. That means if a node dies, the if one of the node dies, then all the other nodes have to work a bit more in order to cope up with the loss imposed by the death of that node. That puts extra burden on the other nodes, and thus the energy consumption of those nodes, because one of the nodes is dead, one of their partner is dead, so all the other nodes have to work hard, and thus they will exhaust their energy real soon. And hence the lifetime of the network is again of supreme importance, that whenever working on a wireless sensor network or a sensor based IoT network, our objective is to optimize the network lifetime and improve the network lifetime in such a way that the network remains stable. We'll talk about the stability period, what a stability period is, but the objective is that we enhance the network lifetime of the network of the wireless sensor network and aim for a maximum stability period. Now, the third desirable thing is the in-network inference without loss of information. Now, as in-network inference techniques are techniques which rely on in-network processing of data. In-network processing of data, that means that involves a bit of computations at the node's end, but you will see that the computations involved, okay, let us try to understand it like this, that if a node performs certain computations and is able to generate, let us say, you might be familiar with the term aggregation. So data aggregation is nothing but calculating the average, calculating the maximum sum, or certain operations we apply on the data, on the data we have at hand. So if I say we apply a data aggregation task at this point, now what we are saying is that we received, let us say, 100 KB of data till this point, and we have from this path also, from this path as well, from this path as well, from this path as well, and at this point we aggregated the entire data from all the received paths, and we forwarded a single packet from now on. So this node will receive a single packet now. So what we have done, we have necessarily done, is we have reduced the data size, and this in turn reduces the transmission cost, the computational load of the other nodes in the path. So this is what we mean by when we say network inference or a network inference methods. Now, so the entire objective is to make use of in-network computations and in-network processings to optimize the network's performance in terms of lifetime, in terms of event detection, in terms of loss rates, or whatever. So, okay. Once we have these three desirables, now these three are the most important desirables in any sensor network or in any sensor based IoT network. Oh, okay. So, but for achieving these objectives, we have to also understand these objectives are not so easily achieved because there are so many constraints in a sensor network. We have talked about few of the constraints, and we'll talk about some of the constraints even now. So, for instance, the one of the most important constraint which I'll be addressing in the solutions, I'll be providing a solution for that, is also the energy hole problem. Now, the energy hole problem is very simple to understand, and you'll understand how simple this problem is if you just pay attention to this figure over here and try to understand this, that there there are, let us say, there are multiple events occurring on in this field, right? And this node is also sensing event. This node is also sensing an event. This node is also sensing an event, and all these events are being reported to the sink, right? And once we say that all these events are being reported to the sink following a similar path like this, so, and all these paths are through this node, or through this node, or through this node. Let us say this entire, say, area is divided into, this entire area is deployed with sensor nodes, and we have then these nodes, this node, this node, this node, this node, to be the to be a common node in many of the paths reaching this sink. Now, what you can see is, if you can even see this figure, then you can see that if there are multiple paths going through this node, then what does this mean? That this node will exhaust soon as compared to all the other nodes. So all the nodes closer to the sink, they die or they exhaust really soon if they have to work very hard, if they have to transmit, if they are to be responsible for transmitting the data for every other path in the communication chain, then and if they are doing their job properly, then they will exhaust soon, because the data transmission requires energy, and all the nodes in close proximity to the sink will start dying one by one. So what happens is that a bottleneck is created over here, that the entire network is alive, but the bottleneck load on the nodes in close proximity to the sink is significantly high, and hence all the nodes in close proximity to the sink die relatively quickly as compared to the other nodes in the network, and hence a hole is created over here. And this problem is known as the energy hole problem, which is caused due to the uneven load distribution on the nodes. I hope this energy hole problem is clear. We'll talk about this in a bit detail in the upcoming slides as well. But for now, I hope this is clear. So again, the next this was the first constraint, that there is this energy issue which needs to be addressed in any solution which we try to develop. That is, a load distribution method should be there, so that this energy hole problem, or this constraint does not affect us in achieving the objectives. So the next thing which we need to overcome is the amount of transmissions in the network. Now, amount of transmission is high. The number of transmissions in the network can be significantly high, because let us say it is not the case that every time only a single event will occur. There are applications, there are so many applications, and you can simply think of this as a network is never deployed with the objective that one event will occur at only at a given time. There might be the case that there are multiple events occurring simultaneously, and similar events are occurring in simultaneously, and once If this is true, then you can always imagine that multiple nodes start transmitting their data to the sink. Now, when multiple nodes start transmitting their data to the sink at a single time, yeah, because of the simultaneous nature of the events, you can imagine that multiple nodes trying to send their data to the sink, and this results in huge number of transmissions in the network. And because of this, you, as I have already said, the nodes have limited computational capability. The nodes have limited bandwidth. The nodes cannot be burdened with exhaustive tasks, and hence, and now you can see that there are multiple nodes trying to send the data to the sink simultaneously, and this results in large number of transmissions, and hence large number of transmissions require large amount of energy, and hence the node or the network becomes unstable. So apart from these two constraints, there are certain other constraints which we need to discuss. That is, first, the sensor nodes are scarce in resource. That is what we have already discussed. That the nodes have limited computational power, limited memory, limited energy, and all these, because of all these factors, the nodes cannot be burdened with heavy computational tasks. Now, the failure prone feature of sensor nodes, that is very, I would say, that is quite obvious by the idea of the sensor networks, and in which they are, the applications in which they are used. For instance, the difficult terrains in which they are deployed. For example, in a forest, in enemy combat situation, or in certain situations, the nodes might die because of so many reasons. So if a node dies, that means the node has failed to sense and report a specific event, and hence it is very common that these nodes fail. Now, the failure prone feature of the sensor nodes and node failure can be considered one or the same thing. But it has to be understood that if a node dies, the node will not be able to transmit again. But if a node has failed to transmit the data at any point because of certain reason, and the node is not yet dead, then the node might start transmitting again after a moment of time. So that is also that is also to be considered while developing solutions for this. Now, before I start compressive sensing today, and how this was a brief idea about wireless sensor networks. And before I start what compressive sensing is, I would like to open the forum for discussion. If any one of you has any questions, then please feel free, and you can ask any question or any queries if you have. Anyone? Please, if you can start, if you can raise your hand. Okay. Nandini, you can ask the question, please.
Sir, hello, sir.
Yeah.
So, in data aggregation, sir, the data loss is going to occur.
Yes, that's true.
Yeah. Then, what is the use of collecting the data, sir?
One of the major drawback of data aggregation is that there is some data loss involved in that. But the advantage, if you compare the kind of data, the disadvantage imposed due to the data loss and the advantage received due to the significant compression which we receive at that point is significantly high. Yes, there is a cost associated with it, but that is the drawback of data aggregation, that there is some data loss at this point. But the amount of compression we receive from that point onwards is significantly high. It helps us to achieve a better lifetime of the network. So if we are not talking about very precise data, for instance, in data aggregation, if you calculate the average of all the data, data points, then the individuality or the data identity is also lost, right? If you have 38, 39, 40, 41, 42, 43, 44, these as data points, and you calculate the average, the entire average of this will come to, let us say 41, then the individuality of the every data point is lost. So this is one of the drawback of data aggregation. But the compression which is received at this point is significantly high, because in this network we are aiming for a better lifetime. We are aiming for reduced number of transmissions. So if that is achieved, then our purpose is solved. But yes, there is a drawback with this data aggregation technique, that there is a data loss. Is it okay?
Okay, sir. Sir, actually, I'm doing a PhD on this data aggregation in wireless sensor networks, sir. That my sir is not agreeing, sir. If data loss is there, why you are going for this one?
So if you are doing data aggregation in wireless sensor network, there are many techniques. I will be discussing compressive sensing just now, and you will see that data aggregation has a drawback. It is one of the in-network inference technique which is quite popular, right? When we talk about compression technique as such, the data loss is there, right? That is okay. But in a wireless sensor network, as I said, the application which we are talking about has different what should I say, demands, right? We need, let us say, we need a precise location of an object. No, that has to be accurate, right? So if that is the case, we cannot afford to lose any of the data. So in that case, depending upon the application, that might not be possible. But as far as data aggregation is considered, if you are going with data aggregation, there are so many techniques where you can have very minimal loss of data and yet optimize the network transmissions and performance of the network. So once you see this compressive sensing technique, which we are going to discuss today, you will see that this is a significantly better method to optimize the performance or to compress the data. Data aggregation might be considered as one of the compression techniques. So this compressive sensing is much better technique as compared to. Sorry, Khyati, can you mute your mic? Khyati? Okay. So,
Thank you, sir.
so any questions? Any more questions I need to say? So Nandini, is it clear how data aggregation is, that is the
Yes, sir.
drawback, that is the drawback to data aggregation, but the advantages associated with it are much higher. So,
Okay, sir. Thank you, sir.
Okay. So let us proceed further. So we have now a fair idea of what wireless sensor networks are, what are the primary drawbacks of these what are the inherent constraints of these networks are. Now, I'm going to talk about a specific compression technique which we have used in image processing, signal processing from long ago, but we have introduced this method into wireless sensor networks and sensor-based IoT networks in recent past. And since then, it has been used in so many applications and so many ways it has been used. You'll be surprised to see how a technique which was evidently present with us, and but we hardly thought of using it in all the other applications. So we will talk about the compressive sensing in detail, but as you can see, the compressive sensing finds its application in different domains. For instance, the computer science, information theory, signal processing, circuit design, optical engineering, biomedical imaging, and many more applications in which there are many more applications in which compressive sensing is being used today. So to understand compressive sensing, what I'm trying, I'll explain the idea of compressive sensing in a bit detail, but try to understand the idea of compressive sensing in this way. This is a very simple example, and I hope that this will be able to solve any doubt about compressive sensing. Now, the idea is, let us say I captured an image, which is, let us say this, right? And when the raw image which I captured has so many data points, right? So many data points, and hence the size of the image is, let us say, 15 MB. Now, this image can be compressed into a smaller size, right? Any standard compression technique can be used. Let us say I have used the JPEG compression, and I have reduced the size of this image from 15 MB to 150 KB. Now, what I have done is that in the raw image, I captured many data points, right? I have acquired so much information, which is when I look at it, I'm shocked to say that, but okay, I have this much information, but I don't need all this information to represent this image. So what I have done is I have collected massive amount of data, but what I need is a very significantly smaller amount of data to represent this image. So I have compressed this, I have represented the same image into a much smaller form using much smaller number of data points into a compressed form, that is reducing the size from 15 MB to 150 KB using smaller number of data values. What I have done is, although I have captured a large amount of data, I have thrown away some of the data points, and I have discarded these values, and I have represented this image into a compressed form using smaller number of data points. Now, what the thing is, the idea is, one would ask, if I'm going to discard most of the elements, if I'm going to discard most of the data points, if I'm going to discard most of the captured data, why capture it all? Why I should capture this amount of data when I actually need only this much data to represent this figure? Isn't it an obvious question that why go to the why go and purchase a 1,000 rupee product when you are going to throw 800 rupees of it into dustbin, and you are going to use only 200 rupee of the content to represent something? So that is what the idea is. If we are going to capture this entire image, if we can represent this entire image into this size, why go to the trouble of having this much number of data points into the during the capturing phase? Why are we going to capture it? So this is quite a normal question anyone would ask. So this is what compressive sensing answers. So it is more or less on this idea, the idea of compressive sensing was built, that if only this much information is needed, why trouble ourselves to capture this huge amount of information, and if we can represent the entire information in a significantly smaller size, right? So if I say this in a different way, then I would say that in a normal scenario, what happens is we capture an image, we take some samples of it, and we compress it, and then we store it, right? Or transmit it. So, and when once this captured or this compressed image is received at the receiver's end, what we do is we receive the data, we decompress it, and we obtain this. So this is what will be addressed by compressive sensing. This fundamental question will be addressed by the idea of compressive sensing, that if we can acquire, just if we can find out a way that only a portion of information is, if only a portion of information is required, why go to trouble of transmitting the entire data set, right? Why going to the trouble of transmitting the entire value when only a sample of the data is required for representing the information. Although I would say there will be some loss in this entire process, which this compressive sensing idea, when we compress the image and we recover it, it will not be the case that you compress the original image was 1, and you will at the receiver end you will also receive 1. It will be 0.98 or 0.97, so it is a lossy compression, I must say. But the result is significantly, but there is a data loss, but the entire the result is significantly better as compared to all the other compression, most of the compression methods we have, which we have witnessed till date. So the idea of compressive sensing is very clear. Now the idea of compressive sensing is very clear, and that says that if, now try to understand this with the in terms of signal, then I'll try to explain it with the in terms of wireless sensor networks data. Now, since this idea came from image processing and signal processing, hence the definition is in the terms of signals and that sort. But try to understand it like this, that if a signal can be represented by a fewer samples, right? Can be, if a signal is sparse in a domain, what I mean to say, if it is possible to have a sparse representation of a data signal, then if it can be represented in a sparse domain, then relatively less number of samples are required for recovering the original data, if we find a way somehow to transmit the data to the destination. Now this entire definition which you are seeing over here is the general definition, and it has been taken from a paper which I was studying. But in order to make you understand this entire thing, let me explain you this, that this is the entire representation what I am talking about. If we can have a data, now this is the data. Now if it is possible to have a sparse representation of data in some domain, right? If we can have some domain psi as in which this data is sparse, okay? Once we have a known domain that in which this data is sparse, if it is possible. Now this condition has to be met. It is not necessarily true for every kind of data, but if we can identify that if a data is sparse in a certain domain, then we have this, this is what I was talking about. Okay, just my Okay, I hope all of you are able to see my screen. So this is what I was saying, that if it is possible to have a sparse representation of the data, then this data, then this sparse representation can be written as x is equal to psi s, where s is the signal and psi is the representation or the transform matrix in which the data is sparse. If we can have this representation of the data, then we can compress the data in such a way that only a significantly small number of samples are required to be transmitted to the destination, that is z is equal to phi into x. This gives us a significantly small number of samples to be transmitted to the destination. Once this data reaches the destination, then this significantly small number of samples can be used efficiently to recover the data by solving this convex optimization problem, which is a simple optimization problem of L1 norm, given that this entire condition has to be true. That is, this signal S or the data S has a sparse representation in a domain psi, and when we if this can be represented in a matrix form, then if x is equal to phi into x, this phi is the representation matrix or the sample matrix or the sample basis matrix. If we can have this, if this is possible, then we can have phi into x and whatever is obtained as z. Now this z can be used, this z is a relatively significantly small number of sample of the original data, and once we are able to have z at the destination, then this z can be used to recover the original signal or the original data with a significantly high number of accuracy. Now this figure, as I was saying, this is the data. I have taken this animation from one of the authors, which have shown a pioneering research in the area of compressive sensing, and they were probably the few of the first researchers who visualized this idea of using compressive sensing into the domain of wireless sensor networks. So the idea is very simple. If this is possible, that is, if x can have a sparse representation in psi, then we can have phi into x, and which becomes, as you can see, it is quite evident that n over here is the size of this matrix, right? M is the size of this matrix. Now, once we have the product of these two, then what we have is K, and you can see how the size of this N, M, and K is related. So this is the entire idea of compressive sensing, although it would be unfair of me if I say that the idea of the compressed sensing is just confined to these 2 or 3 slides which I have used, but I would recommend this as one of the most important and one of the most promising compression techniques or in-network compression techniques. Rather, it would be, I would say this, and this is totally my personal opinion, that I would say rather than any other data aggregation technique, we can have this compressive sensing as one of the most important and significantly better compression in network compression and in network inference methods, which has been proposed and used till date. So there are 3 problems which we are going to address and which we are going to give solutions for. The first problem which I am going to address is the data gathering problem in wireless sensor networks. And if many of you are working in the area of wireless sensor networks, you must have seen what is the primary problem in data gathering of wireless sensor network is. The primary problem is the energy hole problem, which I just explained. This is what I was telling you. What energy hole problem is: you start at this point, you start transmitting the data to all the neighborhood nodes, then this node transmit to its neighborhood node, and similarly a data transmission path is established, right? Now what I'm trying to say is that, once you see the figure highlighted over here, this node is going to do most of the work, because this is what is going to happen. This is the sensor node 1, this is the sensor node 2, this is the sensor node 3, and this is the nth sensor node, and here is the sink, let us say. Now D1 is the data transmitted by S1 to S2, and S2 transmits what S2 is doing. S2 will transmit D1, the data of the previous node and data of itself. And then what D3 will do, data of itself, D2, data of D1. And when we take this number forward and we come up to the nth node, it is quite simple that D1, D2, D3, D4, D5, D6, whatever is the nth number, this will have to transmit the data this will have to forward the data in just like this manner. And hence, this is a chain topology, and this is the basic problem that because of which any data compression technique is applied. Now, as one of you was just asking, why use data aggregation at all? So you can see why use data aggregation at all, because the sensor node S1 and S2 and S3, you see that the data sensed by S1, the data sensed by S2, and the data sensed by S3 are not going to be that different, because they are correlated. If there is some degree of correlation, if you are going to calculate the correlation coefficient of these three, you will find that these three are highly correlated, and the values D1, D2, and D3 might vary very they might not vary at all, or they might vary in a very small number. The variation is very small in D1, D2, D3, right? And similarly, all the correlated nodes, if I say about S1 and S2, I hardly think there is any difference in the value D1 and D2, or even if there is a difference, that will be significantly that difference will be very small. And hence, if the difference is very small, then how it solves our purpose of optimizing the network performance of transmitting two signals or transmitting two data packets of almost the same values. Like if we are transmitting D1 as 41.8 and D2 as 41.81, what difference does it make? D1 and D2, then they are so much correlated that they can be aggregated into a simple value. So although there is once this is processed at several levels, the data aggregation suffers some data loss as well, and loss of individuality as well. And because of this, certain data aggregation methods are not preferred in certain applications, but that totally depends upon the application of this data aggregation. But in a general scenario, when we say, then you see the importance of data aggregation, that if D1 and D2 are so correlated, then why send D1 once and then again D2 again? Because this transmission is significantly affecting the lifetime of S2, S3, and all the nodes to come in the communication path. So this is the basic idea of a simple chain topology, that once a node starts transmitting in a simple scenario, this is what is going to happen. And once you see that this is the sync node, and this is the nth node which we are talking about, then you see that S1, the data being transmitted between S1 and S2 is D1. However, the data being transmitted between nth node and the sink is 1, 2, 3, 4, 5, 6, 7, and similarly this goes on to n number of transmissions. So once I say that the bottleneck, the global communication cost can be given by this, but the bottleneck load means all the nodes in the close proximity of the sink will be sending n number of transmissions, isn't it? Once you say that these nodes will be transmitting n number of transmissions, then what is quite evident that these nodes are going to die out fast. These all the nodes in close proximity to the sink will die fast as compared to all the other nodes. These, because D1 is a significantly small number as compared to n over here, and hence S1 and S2 will remain alive. However, nth node will die. So this, if this happens, this creates the, what we were talking about, the energy hole problem. However, once with the idea of compressive sensing, what we do is, rather than sending one transmission from every node, we send m samples of transmissions. Now, m samples of transmissions, that means, see, I've tried to show you over here what the first transmissions would look like. For instance, the first transmission would be this 511 into D1. 11 is the first row and first column of the representation matrix, or the basis matrix, sorry. And D1 is the first sample of the data. Now, as I said, instead of sending the entire data, we are going to send only a sample of the data. Now, sample of the data means how many D1 is the first sample, then D2 is the second sample, then D3 is the third sample, or if I say it like, okay, I think this will help you understand it in a better way. So I'm going to say this is the first sample of the data, 511 D1. So the data which was generated by S1 is D1. And by 511, we are saying that the product of these two, when combined together, we have 511 D1 as the first sample of the data which is being transmitted from the first sensor node to the second sensor node. Is it okay? Okay. Now, if it is clear, then what I'm trying to say is that the idea is to transmit not the entire, not all the data. Rather, it is to send m samples, a significantly smaller number of samples, and with the hope that it will be recovered at the sink in a significantly efficient way. Now, once we have transmitted the first sample of the first data, then you see the first sample of this is combined with the linear sum of these two data samples gives us into a single data transmission. Similarly, once we do this, the idea is very simple. S1, S2, S3 all are combined. Phi 1j, dj, and j is from 1 to n. That is all a linear combination of all these values. Now, this is the first sample only. Now, if I say the number, if I go back to the figure which I was showing you here, n, m, and k. Now, what I was saying is that instead of sending n transmissions, we are going to send only m samples. Now, once I say that we are going to send only m samples, then you see from this animation over here that the second transmission goes like this, then the third transmission goes like this, then the fourth transmission goes like this, and we go for m number of transmissions, right? Now, believe me when I say that m is this m, these number of transmissions, m is significantly smaller than n. N means this n number of transmissions which you are doing at the last node or at the bottleneck load. This n number of transmissions is significantly high as compared to the m number of transmissions at every node. So the global cost is nm. Every node in the path will have to send m number of transmissions. So once I say that every node of the globe of the communication channel will have to send m number of transmissions, then that means the bottleneck load, that means that the nth node will also have to send m number of transmissions, right? But you would ask, this was the basic idea, this was the initial idea with which the compressed sensing was proposed into this scenario. But when I say that this was the basic idea, but this is not 100% efficient, because once you look at this figure, you'll see that only initially, once if we are not applying the compressive sensing method, then you see that this node was sending only one transmission, right? D1. This node, the second node in the communication path, was sending two transmissions. The third node, let us say, was sending three transmissions. So the entire load was on nth node, right? Yeah, n minus 1th node, yeah, n minus 2th node, that the number of transmissions on these nodes were significantly high as compared to these nodes. But with compressive sensing, what we have done is we have regularized the load. We have made a balanced distribution of the load, that is all the nodes starting from the first node to the nth node, all will have to send m number of transmissions. So the bottleneck load is reduced, right? The bottleneck load over here, the nth node will have to send m. As I said, m is a significantly smaller number as compared to n. So the bottleneck load has reduced from n to m, right? The bottleneck load has reduced from n to m, but the load on the nodes which are at the origin of the communication path, yeah, the first or the second node in the communication path has increased, because instead of one transmission or two transmission or three transmissions, now they are forced to send m number of transmissions. So yes, with this basic idea, this idea of compressive sensing was proposed, and since then it has been optimized in so many ways to overcome this problem, which I was just telling you, that the bottleneck will get reduced from n to m, but the load at these nodes S1, S2, or let us say S3 as well, has somehow increased, because we never intended to do that, but the entire method or the entire idea is like that all the nodes have to send equal number of transmissions, so that we can have load distribution, equal load distribution on every node. But this results in, this has an advantage of equal load distribution, which overall helps us to optimize the network lifetime. But when you see that these nodes S1, S2, S3 are going to suffer because of these. So this was the initial, one of the most initial ideas of compressive sensing. So with this basic idea of compressive sensing in mind, there are so many. This was, I think it was proposed in 2005 or 2006. But with this basic idea, there have been there have been so many changes in this basic idea, and this scheme which I just showed you over here is known as the plane compressive sensing. And since then, there have been so many research and so many work done in this area, that advanced compressive sensing methods have been proposed, hybrid compressive sensing methods have been proposed, and there are so many optimized versions of compressive sensing now. So we also worked on this idea of compressive sensing, and we proposed an algorithm which involves a clustering method of hierarchical clustering method, which works on this problem, that why do we need to transmit more at this point, if although we are getting an advantage at this point, but why do we need to transmit more on this point? So we tried to optimize this by introducing a hierarchical clustering method. Now, hierarchical clustering method, I'll explain a basic idea of what this method was, because we are running short on time, because we have to address three problems. So I'll try to give you a gist of what this method is, so that it is easier for you to make the most of the most out of the results which I'll be showing you next. So the idea is to perform hierarchical clustering. Now, on the rather than applying compressive sensing at the initial nodes, now we are not going to apply, see, the basic compressive sensing. Yeah, the plain compressive sensing says that you apply compressive sensing at this point, at the initial nodes itself. On all the nodes of the network, you apply the compressive sensing method. But this is not fruitful for the, although this gives us a significantly better result as compared to a plain data transmission, and the bottleneck load is reduced, but these nodes suffer. These nodes S1, S2, S3, or the nodes which are in the initial of the initial or the beginning of the chain, they suffer because of this. And hence we propose the idea of using a clustering method in which the compressive sensing is not applied at the initial or the nodes which are sensing the data. Once we have significant amount of data, we define a threshold for identifying the data load at every node. Once this data threshold has reached at aggregator node, or a node on which multiple nodes on a node which receives data from multiple nodes, once this threshold is reached, that node applies the compressive sensing method on the data received. Once the data is compressed with the help of the compressive sensing, that is, only random M samples are taken out of it, we start transmitting the data to the cluster head. Or if the cluster head is the node which is performing the compressive sensing method, then what is done is, we know that we know that the the data from a wireless sensor network is sparse in nature. And then for creating this phi matrix, we have used a random number generator for creating unique phi values. So once we have compressed the data with the help of this, we transmit the data to the second level cluster head, where it is transmitted to the sink. Uh, before it is transmitted to the sink, Huffman encoding method is used to encode the data again. So you see, at the first level of the clustering, we apply compressive sensing. At the second level of the clustering, we apply Huffman encoding for data compression. Now, finally, the data has reached sink, and at sink, we don't have any drawbacks such as this computational incapability or the energy drawback, or these are not the constraints at the sink. So we can perform as many computations as we want. So with this algorithm, with this basic idea, we perform the simulation, and the results which we obtained for this were significantly better as compared to all the existing methods. For instance, the load distribution, as I was saying, this will help us in reducing the overall workload of the network. It will help us in optimizing the network lifetime. As you can see, the load distribution analysis, this is the sending activity as mapped on a heat map, and this is the receiving activity as mapped on a heat map. So as you can see, the sending activity or the receiving activity is only significantly higher at a cluster head. This might be the cluster head. This might be the cluster head. So it is significant. It is only high at this point because it is receiving data from every corner of the deployed network. And since at this point we have not applied any compressive method, and since the data is coming in its raw form, hence the number of transmissions is higher. You see the red represents almost 1200 transmissions. So this is representing higher number of transmission, and the blue area which we are talking about is represents the transmissions below than 200. So that is why this graph, when you see, yeah, this heat map, when you see that most of the area is blue or something similar to this, and the red areas are relatively very small and very less. Similarly, these two scenarios, in this scenario we have considered the base station to be outside the deployed area. However, the best results are obtained when the sink is placed or the base station is placed at the center of the deployed area. In the figure A, you see that it is a 200 cross 200 meter simulation in which the sink is placed at the center of the deployed area. And when you see that the load distribution is quite even within the in the entire deployed area. Now, with these two load distribution analysis, you can see clearly that the load is evenly distributed. And when you talk about the communication analysis, the number of transmissions in the network and average number of transmitted packets per node, you will see that the proposed scheme is having the minimum number of transmissions in the network as compared to all the other methods in this comparison. Similarly, average number of transmissions, transmitted packets per node is also significantly less in the proposed method as compared to all the other methods. When we talk about the network lifetime, as you can see, this is what is called as the stability period of the network. That is the point at which the first node dies. We can call this duration as the stability period. Now, if you say during this duration, during the stability period, the entire network was alive. That is, if we have deployed 500 nodes, all the 500 nodes are alive. And at this point, the first node died. That is the 400, let us say I deployed 500 nodes, now 499 are alive. Then this means that the network is not stable now. And as you can see, in comparison to both these schemes, the stability period of this proposed method is significantly high. When the sink is placed outside the network, you see that even in that case, the stability period of the proposed method is high. But the important observation is the figure B, which you can see over here, is that once we have placed the sink in the center of the deployed area, you see that the first node died here, and all the nodes die in quick succession after the first node died, right? What does this tell us? This graph shows us that when the first node died and the last node died, this duration is very small between these two. This gap is very small, and this shows us that the load was evenly distributed. That by the time this node reached its last energy, last remaining energy, all the nodes were almost exhausted. And when the first node died and the last node died, the duration between the deaths of these all the nodes is quite less. And this shows that the nodes had equally consumed their activities, their power. So this means that they had worked equally, they had consumed their energy equally, and hence they died in quick succession after each other. Now, as far as this coverage problem is considered, I'll not go into the details of this coverage problem, but I'll give you a brief introduction and then I'll let you know the algorithm which we propose, because time is running short. So I'll tell you what the coverage problem in sensor networks is. Usually these node, let us say this is the cluster head, and all these are the nodes in surrounding the cluster heads. Now this is the communication range of the surrounding nodes, and hence you can see that C can communicate with G dash, D dash can communicate with G dash, E dash can communicate with G dash, B dash can communicate with G dash, and similarly. So, but when you see that this region A, B, C, D, E, F, these regions are not covered by anyone, right? If we say that when we talk about coverage, then we talk about maximum coverage in a sensor network, because if an area is not covered by any node, and if an event occurs over here, and if no node is covering this region, then this event will go unnoticed, resulting in the overall degradation in the accuracy of the network. So what we try to do is we try to achieve at least one coverage, at least, that is at any point of time, all the nodes will be deployed in such a way, or will be activated in such a way that any region in the deployed network is covered by at least one node at all the times. So with this idea in mind, we propose a scheduling algorithm, sleep scheduling algorithm. But the entire idea is, see, that once we target maximum coverage, maximum coverage means that all the regions in the deployed area must be covered, right? But we do not necessarily need that. We need that because maximum coverage means maximum number of nodes, because at least a significant number of nodes have to be activated at any point of time. So a significant, now awaking, see, the idea is very simple, that if you want maximum coverage, if you want every point in the region of interest to be covered, activate all the nodes, all the deployed nodes. Then in that case, probably if the distribution is even, or if the distribution is fair, then all the area will be covered. Then we have achieved the maximum coverage, right? But we cannot afford to do that, because if we activate all the nodes, then they all are consuming power, right? They all are going to die quickly. Then rather than doing that, we try to do sleep schedule the nodes. Sleep schedule the nodes means that we try to schedule them in such a way that at any specific time, some number of nodes will be active and some number of nodes will be sleeping. Now, all the active nodes are deployed in such a way, activated in such a way that the area of interest, that is the region of interest which we are talking about, is covered. Every portion of the region of interest is covered. So rather than having this kind of deployment, rather than having this kind of node placement, we performed a number of experiments, and we approached this problem geometrically, and we obtained that once let us say I try to merge these three circles, B, C, and G, right? I start bringing B closer to G and C closer to G, right? then there will be a point when these three circles will overlap, right? These three circles will just touch each other. And as I can start increasing the overlapping area, but then in that case, only the redundancy is going to increase. So we performed a number of operations, and we performed a number of computations, and we performed a number of experiments to reach at the conclusion that when the nodes are located at 1.75 RS of the cluster head, then approximately root 3 is the overlapping area, and root 3 is the optimal. We can go on increasing this overlapping area, and suddenly we will find that both the circles or all the three circles are overlapping each other. Like if we go on increasing the overlapping, if we go on increasing the distance between the centers of the two, then the overlapping area is going to change accordingly. So if we if we see that at 1.75 RS, root 3 is the optimal. Yeah, root 3 is the overlapping area with which a sufficient amount of correlation can be achieved within the data. And with this idea in mind, we proposed an algorithm to formulate a set of nodes to be activated in such a way that they formulate the entire, this entire representation is of a cluster. The nodes are activated in such a way that together with the cluster head, they formulate a Johnson circle. Now, the Johnson circle is very popular concept, but we try to activate the nodes in such a way that all the nodes in combination with the cluster head formulate a Johnson circle in such a way that these three circles, let us say G, A, and C, they touch each other at only one point, and the area of overlap between the three is not more than root 3. And it is let us say G is the center of this sensor node, and C is the center of this cluster head. Then the distance between these G and C is 1.75 RS. It is not exactly 1.75 RS. So for this was the scheduling part. Now, as far as the compressed sensing part is considered in achieving this coverage, what we did is the entire awake cycle was partitioned into a smaller number of time slots, and these time slots were randomly chosen and transmitted to the sink for further processing. As you can see, this is the entire awake cycle: T1, T2, T3, T4, T5, T6, T7, and this goes on like this. Let us say this is a awake cycle which has the samples T1, T2, T3, T4, T5, T6, T7. Now, ideally, what should I do? Yes. Okay, ideally what should I do is that I should transmit T1, T2, T3, T4, T5, T6, T7, all the data from all the time slots. But as we have seen that transmitting all the data is not important. We can get the result even if we transmit a significantly smaller number of samples. Like we can transmit, instead of transmitting n number of data points, we can transmit only m samples, m random samples. That is what is written over here, is that entire sense data is partitioned into smaller samples, and for reporting the sense event, m random samples, data from m random time slots is sent to the node by the cluster head. Now, once we are able to transmit m random samples as the following the compressed sensing mechanism, we can have significantly better performance. This will be shown with the help of the results as well. Now, if I had time, I would have explained this, how this works, but I'll quickly jump to the coverage. You see the coverage result, the proposed algorithm receives maximum coverage as compared to all the other compared algorithms, and it was able to outperform all the compared algorithms. Similarly, in terms of network energy consumption, the proposed method had significant advantage of over the two schemes in comparison, and similarly in the data transmission analysis as well. I'll be skipping the okay, I'll be skipping the matrix completion part, but because we are running short on time, so I'll be talking briefly about detecting important events. Now, this is the third problem in which we have applied the compressive sensing mechanism, and I would show you what the basic problem is. Now, basic problem in which we have targeted is very simple. That consider a scenario in which there are multiple events occurring simultaneously. For example, a surveillance system. Consider the example of a surveillance system in which multiple people are coming every now and then, right? Let us say at an airport. Now, when we are monitoring the security feed, then we see that there are so many people coming into the airport and going out of the airport every now and then. So there are multiple events occurring. Multiple peoples are coming in front of the camera and moving away. Multiple people are coming inside the airport, going outside the airport, and they once in a while they come inside within the frame of the camera, and we are monitoring this feed. Now, the important thing is that all these people can be a potential threat if, let us say, their hand movement is considered, their gait pattern is considered, but we cannot alert our security system, or we cannot alert we cannot involve human intervention if just because someone waved hand at someone, right? So we need to identify the events. Not all the events, these are all events, but we need to identify the events of importance, right? The EOI, which I am saying over here, is a specific event of interest, which I say that out of all these events, only few number of events are important, and hence we need to identify these events. And once we have identified these events, we have to be sure that these events are actually happening. We cannot miss these events, and we cannot deploy security measures to prevent the activities, even if unless we are completely sure. So to do that, we need to obtain a spatially correlated data, and spatially correlated data means we need to activate more number of nodes. We need in that specific region. That means more number of nodes will start transmitting the data, and more number of transmissions means increased network traffic. That means decreased network lifetime. So what we tried to do is we proposed an algorithm to solve this entire thing, and we worked on this with the help of the compressive sensing method. We tried to obtain the solution for this problem. I don't have time to explain this, so I'll try to show you the results, so that you can refer to this paper, and you can see we have published this paper as well, and you can refer to this paper to understand the idea behind this entire method. So I'll quickly jump to the results so that you can see how this has helped us. See the in-network transmissions. As you can see, the in-network transmissions with the help of compressive sensing, this we were able to achieve very conveniently, and this is a very significant result, that the in-network transmissions are uniform. They might be a bit higher, but they are uniform. Now higher because when we activate more number of nodes for obtaining spatially correlated data, the number of transmissions might be high, but then again they are uniform. So again, the lifetime analysis, you see that the number of the residual energy of all the participants is significantly, is clearly high as compared to all the other nodes in all the other algorithms in comparison. Now, this is the most important result, which is the accuracy rate, rate of true positive, false alarm rate, and area under coverage. And you can see that the performance of the proposed scheme, when I say that the accuracy rate, now you see the detection accuracy is the most important result when we are talking about accurate event detection, right? So the detection accuracy is very high. The rate of true positive is even higher and with a small deviation, and the area under coverage is very high, and the false alarm rate is very, very low. And this is what is expected from any event detection algorithm. That is, the accuracy rate should be high, rate of true positive should be high, the false alarm rate should be low, and area under coverage should be high. So we also compared the runtime of different algorithms. I'm skipping this part. So matrix completion in wireless sensor networks. So I'll not be discussing this. So this is, so finally, I'll conclude my session with this, with these remarks, that compressive sensing is one of the most important methods which we have seen in the past 20 or 30 years or so. And they have been this method has been evidently used in so many applications in of image processing and signal processing, and we are now using this in wireless sensor networks as well, and it has been widely explored. Now there is a lot of potential in this method, and this can be used for localization as well, target tracking as well, and there are so many applications in which this is being used, but there are so many optimizations which can be done and can be used in the existing schemes in wireless sensor networks as well. Again, it will be good to see if machine learning and deep learning approaches can be combined with compressive data gathering for optimizing the network performances. Now, compressive sampling and compressive sensing can be a game changer in the Internet of Things technology. And finally, the matrix completion algorithms. The matrix completion algorithms are a significant problem in themselves. But if we can implement a solution of matrix completion for IoT network, that would be a great thing. So thank you all. That will be the end of my session today. So I am open for questions. If you would like to ask anything, then please do.